All right, so you got your note organizers to fill in what we do on the screen. Okay, so we're going to pull 4 important concepts out of the equation A equals F over M. Okay? Now, this actually is wrong. Why would I put something wrong on the screen? Okay? So, you guys have maybe heard this. F equals M times A. Alright, and that is in fact wrong. Okay? If you were ever taught that, it's wrong. You were lied to. F does not equal MA for sure. Okay? So, Newton's second law, you might have been taught that. You might have been taught force equals mass times acceleration. Wrong. Okay? F equals MA. Wrong. Okay? No. No. We do not do that. Okay? Need I reiterate? No, please move on, Mr. Hicks. Okay. All right, moving on. So here is the correct Newton's second law. And it looks like I'm just being picky, throwing a net in there. F net equals MA. But I'm not being picky at all. Okay, you'll also see this. Fancy way of saying the same thing. What's this? Well, that's sigma. What does anyone know what it means? Sum of. Yep, the addition of. Okay, the sum of all the forces acting on an object equals MA. That's correct. Alright, now I won't usually use this. I like writing out F net. Okay? Now, what's net mean? Okay, how many of you have jobs? Okay, the pay that you actually get to keep, what is it called? Net. Net pay, net income. That's right. Okay, now here's kind of how it works. Picture yourself standing here with a huge butterfly net, like in Miller's class. Alright? And instead of bugs, money is flying by you. Lots and lots of money. It's windy, and you're catching as much of it as you can. Sounds pretty awesome. Okay, now the money that goes into the net is the money you get to keep from your paycheck. All that other money that you miss goes where?
Taxes.
Uncle Sam, the man. Taxes. That's right. Okay, and then if you're my age, also goes to really boring stuff like 401ks and 403bs and retirement and health insurance. No, the kids part, that's in the net. The kids get the stuff that's in the net. They don't get the tax stuff either, but yeah, there's that too. Okay? Alright, now with forces, we're talking about kind of the same thing. Okay, so let's say we got an object like oh, this will work. Okay. Let's say we got like this metal bar or something. And I go up to Sawyer and I'm like, hey, let's play tug of war. Okay? And let's pretend we're tugging the same amount of force. Alright, so nobody's winning. And it's a dead standstill. Okay, what is the acceleration of the bar?
0.
0. Okay, so what is the net force on the bar?
0.
0. Okay, our forces are canceling. Now, let's say Sawyer just is sick of losing to old man Hicks. Okay, what's he do? Okay, alright, now it accelerated in that direction, so F net would be some amount of force in Sawyer's direction. And to find that, we would take his force, we'd subtract my force, the leftover force would be the net force on this, or the total force, right? Okay, so it's the total force. Alright, units. We already talked about this, okay? Units of any force, newtons. And we're doing a mass in kilograms times an acceleration. And so if we put this all together, we got newtons equals that whole thing over there. Alright, so the Newton is really a simplified unit. It comes from that, but that's a pain to write. So we write what's called the common unit, and we just write a capital N. Okay, and the fundamental units, there you go. Okay, now did we do the mouse thing? No, we didn't. Okay, hold your hand out. I'm gonna think this is dumb, but it works. Okay. Alright, now what would a Newton feel like in your hand? If I came around and gave you a small, gray, fuzzy mouse, that would be 1 Newton. Okay, some of you are like, ew. I saw one person go like that. And then I saw another person go like that. I can tell a lot about your personalities for this example. Okay, that would be about 1 Newton. Okay, now what if I do this? How many Newtons? You guys can stop the mouse. Okay, how many Newtons am I experiencing right now? 9.8 Newtons, because this is 1 kilogram, and we are in Earth's gravitational field, so it's 9.8. Alright?
So if you had 2, would it be like 18 something?
It'd be 19.6. That's right, because now I have 2 kilograms times 9.8. Okay, and we'll do a lot with that later. We'll talk about W equals mg. That's how we calculate weights. Okay? We take the mass we are talking about and we multiply it by whatever gravitational field we are in. Most of the time we'll be talking about Earth. Alright, now if we say that Newton's second law is just this equation, then we don't fully understand it. To really understand Newton's second law, you have to understand 4 things, hence the 4 parts in your notes. Okay, so the first part, let's write this down. We have a constant force. Acceleration is inversely proportional to the mass. Okay, so that means this. If I rearrange this for A, meaning I say A is equal to F net over M, M's on the bottom of the fraction. Alright? So when mass goes up, when this gets big, what happens to acceleration? Goes down. Hence the inversely proportional. Okay, now if mass goes down, acceleration goes up. Works the other way too. Here's an example. Let's say we got a motorcycle that is 100 kilograms. And it has an engine that can produce a force, some force, we don't care what it is. But it can accelerate at 10 meters per second squared. That's actually a really high acceleration for a motorcycle. That would be intense. Okay? And let's say we take the engine from the motorcycle and we put it in that car. Hence keeping the force the same, right? The force of the engine, as long as we're applying the same amount of gas and stuff like that, we're going to get the same force. Okay, how big did the mass jump here? Times what? Times 10. Okay, so if mass goes up by a factor of 10, what should the acceleration do? Down by a factor of 10. Okay, so we started at 10, 10 divided by 10 is 1. Okay? Alright, now let's get even more ridiculous. And let's put the engine in a trash truck. Same motorcycle engine. I quintupled the mass here. So mass went up by a factor of 5, what should acceleration do? Down by a factor of 5. Okay, so it's going to be 1 over 5 or 0.2. And notice, in this example, the force is the same the entire time. Okay, we're not changing the force. Okay, here's part 2. Okay, so now we're going to keep mass the same. If we change this, what happens to this? Is what we're talking about here. Okay, so it makes sense. If you use more net force, the acceleration goes up. These two work together rather than against each other. More of this, more of that. Okay, or if you observe more acceleration, that means the force applied, the net force must have been bigger. Okay, directly related. Oh darn, your car broke down. But you have 4 friends. Alright, and so all 4 people are pushing, and let's say they can accelerate the car 1 meter per second squared. But then 2 of them say, forget this, I'm going to Taco Bell. And you're left with only 2 people. Now, what is the new acceleration of the car? Not a trick question. 0.5. Okay? So, we reduce the force to half the force. The acceleration goes down to half what it was. Alright? It works just like you would think it would. Okay. Another example. Here's an airplane. Okay, what's a major problem with airports and engines? The answer is birds.
Yep.
Okay? That's like the most common engine failure, I think. I'm sort of making that up. But if a bird flies in here, we're down to 3 engines. Okay, which is not the end of the world. I think these airliners can operate on 2 and be okay. Alright? They'll probably land right away. Alright, but we just cut out a fourth of the force. So what happens to our acceleration of 2? Goes down, we only have 75% of it now. So our acceleration is now 1.5. Newton's second law. Okay. That right there. Okay, we talked about the gray mouse. We can also think of a Newton like this. If I want to accelerate this at only 1 meter per second squared, that's a kilogram. I have to use 1 Newton of force to do that. Okay, now gravity. Let's say I drop this thing. Okay, I let it go. How many newtons are we using? 9.8. Okay, just like if we were holding it. Alright, well gravity's doing the 9.8. Okay, so if the acceleration's 9.8, then we are using 9.8 newtons. If it's 1 kilogram. If it's 2 kilograms, alright, like this over here, does gravity need to use more force on this? The answer is yes. Okay? Now, what is the same for these 2 things if I drop them? Acceleration. But the force is not the same on these 2 things.
So the force be double because that's 2
The force has to be double. Because this thing's more lazy, right? It's more sluggish according to Newton's first law. So if I'm going to drop these, gravity has to work harder on this to get it to accelerate at 9.8. Okay, so the forces are different, but the accelerations are the same. Okay, part 3. Part 3 says when F net is 0. Okay, what's the net force on that? 0. That's right. Okay, but are there forces on it? Yes, gravity's acting on it, and then what other force? Weight's the gravity. Yep. Okay, the table. Alright, and we're saying support there. Okay, we call support force normal force. You don't have to write that down, we'll cover that later. Okay, but this produces normal force. So the forces are balanced, they cancel, F net 0. That's easy to see. Okay, now if this is 0, what does this have to be? 0 as well. there's no acceleration, so we can say this. Acceleration equals 0 implies net force is 0. If the thing is not accelerating, net force is 0. Now here's where it becomes tricky. Here's a question for you. Can we have a moving object with a net force of 0?
Yes.
Hearing some yeses. Okay, give me an example. If you say yes.
It's like on, like the Earth, like we're on the Earth, so we're moving, but we're still zero.
Okay. Yeah, and then we can talk about moving relative to what? Yes, we are moving right now. Okay. We are moving relative to the satellites, to the moon, but we're not moving relative to our desks. So yeah, we could talk about moving relative to what? Okay, if I say, oh, there's a car going 75 down the highway right there. Is it accelerating? No. Constant speed is 0 acceleration too. So we can't have moving things and have F net be 0. So here's an example. There's a plane, let's say it's going 500 miles an hour. Alright? There are forces on it, okay? The downward force is what? Gravity. The upward force is called lift, which we won't really deal with for a while. Okay, and then horizontally there's forces too. We got engines, we got 4 of them. Okay, and they're all producing one force. We could add them all up and get the total forward force that we usually call thrust from the engines. Okay, now counteracting those red vectors is another force in this direction. What would that be, do you think?
Air resistance.
Yeah, air friction, air resistance. So, acceleration equals 0 implies net force is 0. We take that, we stack those up together, and they cancel out. There are 4 forces acting on this, but the total force is 0. Okay. What happens if we go down to the beach? We lower our altitude. The air gets more dense, thus making which of these forces bigger?
Air resistance.
The blue one. Okay, the air resistance is going to grow because we're literally, as we fly through lower elevation, are running into more air particles. Okay, so the pilot is going to have to increase the throttle to increase the engine force to keep the plane going at constant speed, or else we'll slow down. Alright, now this happens gradually as they lose elevation, of course. Okay, but F net 0. Okay, part 4 is the last part of the thing here. Alright, here's what we're saying. Acceleration and F net are in the same direction, always, 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 no exceptions. Okay, some examples. Okay, here's a car. Alright, now I'm going to have you guys point. Everybody has to point. Take a side, okay? The car's going to do this. Okay, what's it doing? Okay, point to the direction of the velocity of the car. Everybody's got to do it.
Wait, what?
Point to the direction of the velocity vector. Okay, it was in that direction. That's right. Okay, now point to the direction of the acceleration. That way. Good. Okay, now what direction was the F net? That way. Okay, all 3 of them are working together, right? Okay, now what about this? I'll do it again. I'll do it again. I'll do it again. I'll do it again. Okay, same game. What direction was the velocity vector? That way. Okay, now, it was slowing down, so some people want to say, oh, it's this way too, okay? Alright, what direction was the acceleration? Okay, the acceleration is that way, good. Okay, because if I'm going this way and I want to slow down, acceleration has to slow me by pointing in that direction. So velocity and acceleration are opposing. Alright, what direction is the F net? That direction caused by the brakes and friction. Okay, so acceleration F net that way, velocities that way. Alright, questions? Elaine?
So Fnet is always in the same, Fnet is always the same as acceleration, but
Yes.
force itself like can be both ways.
Yeah, there's all kinds of forces at work here, but the net force is always with the acceleration. That's a really good point. Okay, we can't just pick any force. It's got to be the net force or the total force. All right. Okay, what about with gravity? This right here, a soccer ball goes up and down. That's free fall, right? We've studied that quite a bit. Okay, for the entire motion, what direction is the acceleration?
Negative.
Down. Negative, we could say. Okay, what direction is the net force? Down. And in this situation, we only have one force, and that is gravity. So gravity is the net force. Okay, last example and my favorite. We got to turn on the sound. Okay, sometimes Hollywood does a good job with physics and sometimes a bad job. So you decide right here. Is this good physics or bad physics?
Well, that seems legit.
Okay, anybody got a problem with maybe Newton's second law, part 4? Okay, let's look at this. If we could draw vectors here. Okay, what direction is the F net on Tom?
Wait,
From the
is it
blast.
in there or where?
He's running at us like this. What direction's the F net? At us too, because the explosion happened behind. It's kind of like this. The blast is coming out of the screen. The force is coming out of the screen. Okay, but what direction did Tom accelerate?
Turn it to the side.
At right angles to the net force. Okay, they didn't even try to get Newton's second law right here. Okay, that would be like if I exerted a net force on this, pushed it that way, and it went like that. Okay, that's what Hollywood is saying. It's just wrong. Okay, so you're going to notice from this class when you watch movies, things are going to disappoint you sometimes. Alright? Okay, so I think that's all. We'll do that one later. Okay, do you guys have any questions?